In this video, we will discuss thermistors. Let's do another quick review of ideal temperature sensor characteristics. An ideal temperature sensor is accurate, repeatable, low in cost, easy to calibrate, and has a fast response over a wide temperature range. Furthermore, a simple relationship between sensor output and temperature is highly desirable. Thermistors exhibit some of these characteristics. A thermistor is a resistor whose resistance changes with temperature. The resistive element in these sensors is generally a metal oxide ceramic containing manganese, cobalt, copper, or nickel. Thermistors are packaged in a thermally conductive glass bead or disc with two metal leads. Thermistors typically are described with a resistance. For example, you may have seen a 1 kilo ohm thermistor. What does this resistance mean? Well, it means that at some reference temperature, such as 25 degrees Celsius, the resistance of the thermistor will be 1 kilo ohm. This resistance changes with temperature. So, what would happen to the resistance of a thermistor if the temperature increases? Well, it all depends on the type of thermistor that you are working with. Thermistors are typically specified as NTC or PTC. NTC means negative temperature coefficient. Most materials have a negative temperature coefficient and exhibit a drop in resistance as temperature is increased. The behavior of an NTC thermistor is shown in this graph. PTC means positive temperature coefficient. PTC materials have a resistance that increases with temperature. Now, this graph highlights two important differences between thermistors and the integrated silicon linear sensor discussed in a previous video. First, thermistors output a resistance and not a voltage. Second, the output of a thermistor is typically nonlinear with temperature, whereas the output of an integrated silicon linear sensor is linear with temperature. So we now know that a thermistor outputs a resistance. How can we measure this resistance? Well, a resistance measurement can certainly be performed using a digital multimeter. Now, because the output of a thermistor is nonlinear, a special equation is needed to convert the measured thermistor resistance to a temperature. In comparison to the equation for an integrated linear sensor, the equation shown here is not as straightforward. In this equation, T sub R is the temperature in Kelvin. R is the measured resistance at the temperature T sub R. R sub ref is the resistance of the thermistor at the reference temperature T sub ref. A sub 1, B sub 1, C sub 1, and D sub 1 are the Steinhart-Hart coefficients. How can these coefficients be determined? The simplest way of determining these coefficients is to take a look at the datasheet. Steinhart-Hart coefficients for various Vichy thermistors are shown here. The first tasks are to determine the R sub ref and B sub 25/85 value for your thermistor. For example, a 100 kilo ohm Vichy thermistor has an R sub ref of 100 kilo ohms, and the datasheet specifies that this thermistor has a B sub 25/85 value of 3528. At temperatures above 25 degrees Celsius, the Steinhart-Hart coefficients for the 100 kilo ohm thermistor are shown here. Knowing R sub ref and the Steinhart-Hart coefficients, we can then plug in our measured resistance into the Steinhart-Hart equation shown above and determine the corresponding temperature for that resistance. Now, what would happen if you lose the datasheet for your thermistor don't believe the information that is on the datasheet, or would like to verify the coefficients yourself. How could you obtain the Steinhart-Hart coefficients? Well, you could certainly create different temperature baths and first determine each bath's temperature using a different device, such as a thermometer or another temperature sensor. Creating a bath that is at 25 degrees Celsius would enable you to determine the R sub ref of the thermistor. Measuring at least 4 resistances at 4 different temperatures and performing matrix inversion will enable you to determine Steinhart-Hart coefficients. Taking additional measurements would also be helpful in determining these coefficients. So, the output signal of a thermistor is a resistance. However, the devices that you use to record signals in your underwater robot may only be able to take in voltage signals. How could you convert a resistance into a voltage signal? You may have encountered this already. As a review, you can convert a resistance into a voltage using a voltage divider. If you have a voltage source, V sub S, you could create the following circuit and measure V sub out. The voltage divider equation is shown here. You can see that V sub out equals V sub S times R sub 2 divided by the sum of R sub 2 and R sub 1. So, now's a good time for a quick quiz. If you have an NTC thermistor and you want V sub out to increase with temperature, where should you place your thermistor? Should you place your thermistor in the location labeled R sub 1 or in the location labeled R sub 2? Again, the goal is for V sub out to increase with temperature. Please pause the video, give this problem some thought, pick a location, and unpause the video to see the correct answer. The correct answer is R sub 1. NTC means that the resistance of the thermistor will decrease as temperature is increased. You can place a resistor with a known resistance in the location of R sub 2. This will keep R sub 2 constant. Therefore, if the thermistor at the location R sub 1 has a resistance that decreases with increasing temperature, then V sub out will increase with temperature. Here is a summary of the temperature sensors that we have discussed thus far. As you can see here, thermistors have a wider operating temperature range than integrated silicon sensors, and they are also more accurate and have a faster response time. However, thermistors have a non-linear output, and a voltage divider is required to convert the output signal of a thermistor to a voltage signal.